My name is Daniel Crenshaw, and this is my Lab 3 report. The purpose of this lab was to find the mass of a black hole by analyzing a star's orbit around the black hole. We were also supposed to determine or manipulate a spaceship's initial speed so that it would properly orbit around a moon and a planet. The main physics principle we use in this lab is Newton's second law, the momentum principle, and Newton's universal law of gravitation. Here is the main outcome of the experiment. I determined that the mass of the black hole was 5.2 times 10 to the 43rd power and manipulated the initial velocity of the ship so it would properly orbit both the moon and the planet. But the x value was the moon's x value velocity times 5.4, and the y value was the moon's y value's velocity times 1.8. Here are some of the main physics principles used for this lab. The first principle used was the universal law of gravitation. This was used to calculate the force of the black hole and the planet on the orbiting star and the spaceship. We also use these formulas for the momentum principle. F net is equal to the change in momentum over change in time, and F net is also equal to the force of the parallel component plus the force of the perpendicular component. Some other important details for this experiment include the system, the surroundings, and the initial conditions. The system for this first part of the lab was the black hole, and the surroundings was the star. For the second part of the lab, the system was the spaceship, and the surroundings were the planet and the moon. One of the initial conditions for the lab was assuming that the net force on the star is due solely to a black hole located at the origin, and that the time between data points and the trajectory is 1 Earth day in seconds. We were also given that the mass of the star was 2 times 10 to the 30th power. Now here is a simulation of the first part of the lab. We can see that the star is completing a full orbit around the black hole, and that the mass of the black hole is constantly changing. This is because for each time step, the initial velocity and force of the star is constantly changing as well. To find the mass of the black hole, we must first find the parallel component and the perpendicular component of the force of the black hole, and then use its force to calculate the position and velocity of the star. This in turn allowed us to calculate the mass. And here is the simulation for the second part of the lab. You can see that the planet, which is the purple line, is being affected by both the force of the force of the moon and the force of the planet. The combined forces are affecting how it is orbiting both bodies. To do this, we first calculate the distance from one object to another for each object, then calculate the force that both the planet and the moon have on the ship, and use this force to calculate the ship's position and velocity. Some possible errors that may have occurred during this lab are incorrect applications of Newton's principles, like the universal gravitation principle. Now, to explain the difference between net force and rate of change of momentum, it should be noted that the parallel component and rate of change of momentum are technically the same. However, it is easier to observe the parallel component through physical interactions, whereas the rate of change of momentum requires prior knowledge to be known before you can calculate anything. And finally, if a simulation were to include a black hole, a moon, a planet, and a star, all force interactions for every object would be needed, along with the object's mass, initial position, and initial velocity. The most dominant interaction would be the black hole with all other objects. There would also be less dominant interactions between the moon and the planet and the moon. And that is the end of the lab report. Thank you for watching.